How many sandwiches can you make in 5 minutes? 1? What if you made 2 at a time? How about you double that? And double that again. It gets fast real quick, but here's a problem. It's hard to keep track of them. It becomes a hot mess and your sandwiches burnt. Could we somehow avoid that? And why the hell am I talking about sandwiches in the first place?
Well, if you make a good one, not only is it an accurate description of multithreading, but also very delicious.
What is this now? Oh, multithreading. So imagine the stove is your computer. It has 4 places for pans. Each pan is a processor core, and a sandwich is a job or a thread. You can cook one sandwich in one pan on one stove, no problem. But if you got the rest of the stove left, why wouldn't you want to use it? After all, you've got 4 more sandwiches ready to go. This is exactly the situation on our memflow code. Take the value scanner for instance. Here, we have some initial setup, and right after that we jump into this loop that goes through all memory in the program and picks out matching data. Initial setup here is rather sequential, just like the sandwich prep. But then this loop can absolutely be split up and ran in parallel. In sandwich world, this would mean cooking 4 or 8 sandwiches at a time. Alright, but how do we do it? Right here, I have my structs binary, which I changed to allocate 2 gigabytes for testing purposes. We will search for bytes with value 64 and then rescan it with 64. And let's just run it, and let's just see how it goes. Enter password. And it scans. So like, as you can see, we get something like 200 megabytes per second, 220. And then on the filtering step, we have like 162,000 elements per second being filtered, which is pretty good. But I mean, it can be better. How do we do that? So one thing to note is that multithreading should be kind of a last resort, the last step, because with threading you get a fixed amount of performance, like 32x for 32 core machines with perfect scaling. But that's as much as it scales. So if there is a way to make it faster without involving multithreading, that's what you should aim for. And for filtering in particular, there is something. As you can see, we average about 160,000 elements per second. And that something is batching. Batching is very similar to multithreading, like they go back to back. Batching is something we did in episode 2 of the series, and it's, well, as simple as taking the data and splitting it up into small chunks and working on them in one go. So right here, we have this basic loop which goes through matches. It reads the match and it checks whether the match is still equal to the input value. And if it's equals to that, it pushes it to the new match list. So to batch it, we will just define a chunk size. And let's say we process 256 elements at once because it's a very nice round number. And here we will essentially have a chunk in all the matches dot chunks of size, well, chunk size. And here we will use a batcher. And then we will go ahead and go through every element in the chunk and batch it for reads. So how do we do that? Well, we need to go through chunk. We will do batcher.read raw into. We read the address and we read into some buffer. And then we just do std mem drop dispatcher, this is where it will read it. But here's what we need. We do need a buffer to read through. We need to zip it up with a buffer dot chunks of size data dot length, because everything we read is going to be of size data dot length. It will be chunk dot iterator dot zip with that. We have this batch, and afterwards we will do the same loop here, except we will do if buff equals data, then self.matches.push a. So essentially this read line becomes these 6 lines, and this comparison of 3 lines becomes these 4 lines. And the final step is to add to the progress bar not 1 but the chunk size as u64. And here's one more thing. We need to allocate enough memory for the entire batch, so it will be chunk size times data.length. And that's essentially it. That is batching, and let's see how it goes. So this doesn't change because we're not changing this code here. And look at that. Isn't that beautiful? We went from, what is it, 160,000 to 2.6 million, I believe. That's a 16x speed up. Just from batching, and we don't have threading in yet. Let's add multi-threading, shall we? How do we do that? This is where a different paradigm of programming comes into play. It's called functional programming. Instead of performing operations on the data, you describe what happens on the data. Or should I say, instead of describing what happens to one element of the data, you describe what happens to all elements of the data. They sound very much similar because they actually are. An analogy which helps me understand functional programming is thinking of it as building a pipeline or a factory where you have data coming in, stuff happens on it, like it can be transformed into different data, it can be filtered out, it can be split up into smaller pieces, and it could even be combined back in. And then it outputs the data. That's final, transformed, filtered out, good to go. And that's essentially what you have to do with functional programming, and that's what we're going to do right now. So right here, the perfect example is this for loop, where it goes through the chunk, it iterates it, it zips it up, and it compares, and then it pushes to the list. In functional programming, you don't push on the list. What you do instead is do self.matches.extend, and then you pass this whole iterator, this whole chain into this. And there are like a few things you can do with iterator chains. Let's just get this. So in here, what we do is we transform the data. We transform from address in a buffer to just a single address. And the second thing we do is we filter the data. So the transformation is called map and filter is called filter. So a function that does both at the same time is called filter map. And we have the same input as we do right here. And what we do here is just check if buffer equals data, then we return the address, else we return none. And then we just get rid of this and format the code, and this is what we end up with. It does the same thing, but differently. We're doing this because it will allow us to make it, just split it up into threads very, very easily, without even thinking about it. But what you first need to do is convert the entire code into this functional way. So what we need to do is just move self.matches.extend out of the loop. So what you need to do here is turn this for loop into an iterator. And notice how it was 2 for loops in particular, but the output is just one piece of data. So what happens with the second for loop? We essentially take a chunk and split it up into smaller pieces of data, then producing a new iterator on each of these chunks. To convert them back into one pipeline, we kind of flatten those chunks out into, well, one chain once again. So this will be a flat map, which is another operation that can be done on the iterators. So flat map takes in a chunk and does something, and then, well, it outputs it. What we need to do is just return this iterator back here. And that's it. Now, it doesn't compile because it says a variable cannot escape the body, which is absolutely fair because, as you can see, this uses the buffer. Actually doesn't need mutable buffer, but it doesn't matter. It just goes through the chunks of the buffer, which is, well, it is used here. It is being read here. What if you get the next element, but then you call next on this? You risk your data being overridden. So what you need to do, sadly, is you need to collect this output and transmit it back once again. So we use collect into a vector, which is an array, and we just convert it back into the iterator. And once you do that, boom, done. And now this whole loop is functional. It should be just as fast. And then I will show you how to make it multi-threaded. As you can see, it's just as fast. What it allows us to do now is to just make it multi-threaded. And how do we do that? Well, we will use a new crate, which is called Rayon. It's version 1.5, I believe. And Rayon is meant for one purpose, and that is to make these functional iterator chains multi-threaded. And it's very simple. It is a use Rayon, prelude, everything from prelude. It's grabbing the thing and just changing this to instead be dot extend to be par extend, meaning parallel extend. And you go from old matches.chunks, use parallel chunks. And here you could make it parallelize, but we don't need it. What matters here is that we convert this back into parallel iterator. And that's the very essence. Now, if we run it, it should not compile. Here we go. It says, cannot be shared between threads safely. What cannot be shared? It's the T, which is our memory object. You see, right here, this is our memory object, and it cannot be shared across threads safely. And that's the thing. You see, our memory objects that provide virtual reads are actually not thread safe. They have some internal state within them, which would mess up if it was to be modified from 2 different threads. And as you can see, Rust, it prevented us from shooting ourselves in the foot. But what are you gonna do about it? Well, this is where another crate comes into play, and that is a helper crate, which I will link in the description. It's called Rayon TLS CTX, and I have it here in the path. It will be this thing, and yeah, and we've just used a Rayon TLS CTX thread local CTX. we have an error. Oh, path equals. Here we go. What this helper does, it essentially allows us to create a copy of the memory object for each thread individually and do it rather efficiently so that you don't have to copy it very too many times. Essentially what the change is, we do create a ctx equals thread local context new, and what we do is create a lambda which does one thing. It will be mem.clone, and we move the memory object into it. Now it does not have clone because we need to bind clone as a trait that we need for the object, and memflow memory objects usually support cloning. So you have a clone right here, and what you need to do, we need to essentially create here let mem equals ctx.get, and it's an unsafe function. Unsafe is very scary, right? Everyone dares not to touch it, but if you read documentation, it says about safety. It is entirely up to you to ensure that this scope runs only on one thread pool at a time. What that means, well, if you just run it within one iterator chain at a time, it's alright. That's essentially it. And if you like kind of mess it up slightly and have it borrowed twice, like so, it will panic because it is illegal. You can only have one reference at a time, and that reference will be usable and be safe to use in the parallel chain. And as you can see, the same thing is about the buffer. So we will create a let ctx buff equals the same thread local context new, but instead here we do a new, just create a new vector of size chunk size times data dot length, and we don't use a buffer, and we just get a buffer equals unsafe ctx buff dot get. And one final thing is our progress bar is not thread safe, sadly, but we will see results afterwards. So yeah, this is it. We just added parallel extend, we made it parallel chunks, we added this helper which essentially clones the object between threads, and we collect it back in, and let's see what the difference is. If it's gonna find the process, wait and see. Did you notice it? Did you notice it? Let me open calculator. What is it? I think it's 10 million elements per second. Beforehand, we had 2.5 million, I believe. So we have 4x speed up from this. 4x speed up by adding threading. And mind you, this is so much more on top of our initial cute 150,000. We get 67x speed up. This is awesome. This is awesome. You could notice it if we run it again. So this is going slowly. We will tackle it next. And this is nearly instant. Isn't that awesome? Isn't that awesome? Let's take a look at the performance metrics. I made these runs behind the camera, and this here is for, it's for the value scanner, the first scan phase. And we got roughly 5x speed up. The second one here is our value scanner, the filtering phase, and it's also got a roughly 5x speed up. And this here is another run, which got 5.4x speed up. As you can see, they roughly are 5x. And we have 32 cores on our machine, 32 threads on my machine, and 16 cores. And as you can see, these numbers have some variation, but they're roughly capped out at 5x. And it's actually not a coincidence. It's actually governed by something called Amdahl's law. Right here, this is Amdahl's law, and you can read it on Wikipedia, but essentially it states that your code that you're trying to multi-thread will be bottlenecked and limited by part of the code which you cannot multi-thread. And essentially, if you have a perfect scaling, the more threads you have, the better it runs into infinity. If you have infinite threads, it runs at infinity. And that's really cool. But if you have a program which has 0% scaling, like it's single threaded, no matter how many threads you've got, you're still gonna run at the exact same speed. And this here, you can see, is the formula. And you can play around with it. The P is the part of the code which is multi-threaded. So at P of 0, you get the same speed up everywhere. It's 1x, which is the original speed. And if you have 1, it is linear and goes into infinity. And if you have code that is like 50% multi-threadable, and the other 50% is probably some setup code, where does it put us? Well, it puts us at, if you look at it, it puts us roughly at 2x. And if you have 32 threads, it doesn't reach 2x. It tops out at 2x at infinity. And because this here, the number of threads you got gets higher, this p here gets smaller. It gets divided. The p being the parallelized part of the code, which is 0.5, gets closer and closer to infinity, but you're still left with this 1 minus p, which is the single-threaded part. Now, where does it put our code at? Remember, we've got 32 threads, so we're somewhere here. And we've got a 5 to 5.5 times speed up. So, let's raise our parallelization thing until we get to roughly 5. I'd say it's roughly here. 0.83, meaning 83%, if you just verify this. Yeah. 5.18, yeah, this is about it. We've got some variation, don't forget that. Our code is roughly 83% multi-threaded, which is actually really, really cool. Also, another thing is that, remember, our CPU, my CPU, is not a true 13-core machine. It shares resources, so there's a little bit of overhead in that, so we can raise that to roughly 85%, I'd say, which puts us about on the upper range of our variation chart. So yeah, 85%, I'll take it. And this is it. This is essentially it. We've got that hard limit, which we always try to break. But it is a hard limit, and I think it's very useful to know it and understand why your code doesn't scale infinitely. It's because of this. And yeah, single-threaded is any part that is single-threaded, and also all the overhead for dispatching into threads. So keep that in mind. That thread dispatch overhead is real, and it can decrease the p and make your code actually slower in some cases if you have a lot of thread dispatch going on. Just keep this in mind. So yeah, I think this is about it. What we did, well, we made it extremely fast. If we just run it, boom, instant things happening. How did we do that? Well, we used functional programming, a little bit of that, and we used parallelization to make things fast, split up into tasks, and that makes us go roam on a massive pipeline of a factory we're almost done, but there's so much more I wanted to show, so if you're curious about that, a video will come after this one in a few days, which will be an extended version where I'll go through every single part of ScanFlow and make it multi-threaded one by one, starting from the value scanner, the scanning phase of it, then going to disassembler, then going to pointer map, and all that stuff. It's going to be fun, so if you're interested, look out for that. This was a lot to take in, yes, I know, but I hope you understood at least a tiny bit of it. And feel free to ask me any questions, and don't forget to overfollow the like button, which helps the channel tremendously, and hit subscribe for more content like this in the future. Thanks so much for watching. I hope I'll see you very, very soon. Don't forget, my name was Heap. Yours was undefined. See ya.